I want the cursor to take to the beginning of the new line, then it is 0a. That means when you're writing in any assembly level programming languages, now to specify the new line, it should be a combination of both 0a and 0d, and the 0 is to just indicate the termination of my string. As 0, I'm taking it as a null character here. Now we'll come back to this. Now ADR R1 comma text. What I'm doing here now, I'm loading the starting address of my string hello world to R1, and then I'm moving 1 to the register R0. Now LDRB. Now each one is a byte here. This is 1 byte. This is another byte. E is another byte, and this is one more byte. And if I count the number of bytes here, 1 2 3 4 5 6 7 8 9 10 11 12, it's a 12, sorry, 1 2 3 4 5 6 7 8 9 10 11, and including this new line, it is 12 bytes of data. Now what I'm doing now, LDRB R2 comma, and you know this is pre-index with write back. So if I'm not sure, because I have already explained this to you people, pre-index with write back. That means R1 will be incremented by 1, R1 will be incremented by 1, and R1 is updated. So R1 will be the starting address of hello. It is incremented by 1, and then R2 gets loaded with H, and compare R2 with 0, and then you can observe here SWI and not equal to. Now I'm comparing R2 with 0. Why I'm comparing R2 with 0? Because this is a null character. The moment if we get a character 0 to the register R2, I need to stop. So SWI, and this is the condition which is embedded to SWI instruction, SWI write. SWI write, now I've equated it to 0. 0 is the function number which is present. There is a function number with the name 0 which is present inside the kernel, and that function number is responsible for displaying the character which is available in the register R0. Sorry, register R2, because we are loading it to the register R2. The previous register is R2. The character goes to the register R2. What will happen? This will print the first letter H on the screen, and then BNE to loop back. This gets repeated until all these characters are printed along with the new line. And the moment R0 gets copied into the R2 register, sorry, 0 gets copied into the R2 register, 0 minus 0 condition is false, it will come out. And SWI 11 is for terminating the program. So this is one example. Let me execute this and show you. Assemble, build, and then debug. Now I'll just debug this. You will not see the output on the console now. I'll just show you how the flow goes. For seeing the output of this program on the console, you got to execute it from the command prompt without using the debugger like this. Now ADR R1 comma text, you can observe 24. If I just go to this address 24, let me go here, address 24. See, this is what your hello world till here. Now what is this 48? 48 is the hexadecimal equivalent of the ASCII of H, and 65 is for E, and then L, right, next character is L, that is 6C, and the next character is again, that is 6C, and then O, this, and space is 20, hello world, and then you can observe till here. This is the hexadecimal equivalent of D, 64, and you have 0A, 0D, and finally you have 0. Now the starting address is moved to the register R1. Now R0 is loaded with 1. Now this is what I'm doing. And what goes to register R2 is 65. Sorry, this is supposed to be I had to do it as because LDR current pre-increment I'm doing, I should have subtracted this by 1. Yeah, just let a minute, that's it. Let me stop debugging. So it's taking the next character. Let me subtract here 1. So Now what goes to the register R1 is 23. Earlier it was 24, now 23. Now but because 23 plus 1 will do, will pre-increment it, it will become 24 and it will get the first character H to the register R2. Okay, observe now. R0 with 1. Now R1 is this, how much? 23 plus 1, it is 24. 24 is this, and this is the hexadecimal equivalent for the letter H. Now what gets loaded to register R2 is 48. You can see here 48 went to the register. This 48 is nothing but the letter H. When you print 48, when you try to print 48 on the screen, it gets printed as uppercase H. So now compare 48 with 0. So no, this is not the end. Now what this will do, this will print this character on the screen. Now this will not happen since we are doing it in the debugging mode. You cannot see this character on the console or the command prompt. So if you execute this program from the command prompt, you can see the output displayed on the command prompt, just like your printf statement. Now the process is repeating. Now what will happen? So it is R1 is right now 24 plus 1 is 25. It is just memory location. Now what goes to the register R2 is now E. See, 65. That is nothing but E is the hexadecimal equivalent. E is hexadecimal equivalent is 65. And from there I compare 65 E. You can observe here when I drag the mouse pointer to R2, it's not showing me 48, it's showing me E, because 65 is an hexadecimal equivalent for the character E. You can so E I'm comparing with 0, not same, even that gets printed, and the process repeats like this for all until this 0 is loaded to the register R2. So compare 0 with 0, then the process stops and it will come out. Now okay, this is enough, I think. So a later point of time I'll try to execute that program from the command prompt and show you the hello world message gets printed on the console. Now I will go back to the program. Okay, so that's the end of the software interrupts. You don't have much on the software interrupts because you are not using that is the only thing that is specified in the syllabus. There are various function numbers. 00 you understood now. SWI00, what it will do, it will print a character on the screen, and similarly there is a function number to read a character from the keyboard, standard input, that is standard input, and similarly there are function number to read the string, print the string on the screen, and many function numbers are there, especially the function numbers varies from 0 to 255. So many function numbers are present inside the kernel. Now all that is not important for you right now. So next is the program status register instruction. The ARM instruction set provides two instructions using which you can directly control the program status register, that is current program status register and SP saved status program register. Both can be directly controlled using the instructions that are provided by the ARM set. ARM instruction set. So there are two instructions basically. One is MRS instruction, which transfer the content of either CPSR or SPSR into a register. So using this instruction you can copy the content of CPSR and SPSR to the register, and using MSR instruction you can transfer the content of the register to CPSR or SPSR. This you'll be using in order to read the status register, and this you'll be using in order to set the status register. Now RS here means read status register, that is from CPSR or SPSR you are copying to the register, hence it is called read the status register, and this is set the status register, set register, so from the register to CPSR or SPSR. Now how do you perform this read the status register or set the status register? The syntax is like this: reading the status register, and again you can have a mnemonic is this MRS, and you can embed the condition, and there is a destination register. And this what happens here, you are copying CPSR to RD or SPSR to RD, and MSR you can observe here. Now what we do in this, here we copy CPSR to RD from CPSR or SPSR to RD. In this it is we are setting the CPSR or SPSR. Now this is the register which is holding the data that you need to assign to SPSR or CPSR, and this is optional fields again, where you can specify which particular bits of the CPSR or SPSR you got to modify from the RM. And similarly MSR, there is one more. Instead of this is same as this, only thing is you have instead of register an immediate number. Now this fields can be C, X, S and F. If you want to modify the flags, you give it as conditional flag F, and if you want to modify the status, you got to give it as S. If you want to modify the control, you got to give it as C, and if you want to modify the extension, you got to give it as X. And this you already know, this is the CPSR, first 5 bits mode, using which you specify the 7 different modes of the processor, and then the thumb state and fast interrupt, slow interrupt, overflow, carry, 0 and negative flag. And there is one more here, 27 bit, which is the Q bit, and the 24th bit is the Zazzle state bit. I hope you remember all these things. Now here is how it happens. When I say read the status register, this is program status register. Now C is C or S. What you can have here is C or S. If you want to copy the current program status register to destination register, it is CPSR. If you want to copy the saved program status register, it is SPSR. Now the general RD is equal to PSR, program status register, and then move the general purpose register to a program status register. Now I want to copy this to the CPSR or SPSR or CPSR, and inside the bracket I can specify the field, because if I want to change only the conditional flags, I can change. If I want to change the status flags also, I can change. Correct? If I'm changing the conditional flags, I got to give it as C. So status flag I got to give it as yes. And similarly this is same as this, only thing is you have instead of the register, immediate number. Now here I have the example for the same. Now I'm assuming the current CPSR is this, so it is in supervisory mode. You can observe all these bits are 0, and this is 1, and this is 1, and thumb state is also 0. Now MRS, read status, what I'm calling must read status CPSR to R1. What I'm doing now, this current values, I'm just copying it to the register R1. So CPSR is also a 32-bit register, and this is also a 32-bit register, and everything gets copied to this. Now I'm calling this a logical bit clear instruction, BIC, which you already know. It does first register and negation of second register. Now R1, and then 8 I'm taking. 8 in binary, 80 in binary is like this. Now this particular bit I want to clear. Correct? No? So that is the reason I made it as 1. Now I'm using MSR and CPSRC, R1. Now what I'm doing, the value which is available in the register R1, I'm just copying it to this. When I copy that, see here the slow interrupt which was enabled earlier. Now the slow interrupt, which is disabled earlier, now the slow interrupt is enabled. When it comes to the question of interrupts, 0 means enabled and 1 means disabled. Now here it was disabled, now here it is enabled. Why it is enabled? Because I gave this as 1, and when I make this 1 here, and when I apply bit BIC, so this particular bit in register R0 will be 0, R1 will be 0, and this is 0 now, and we have the slow interrupts enabled. So next is the coprocessor instructions. Coprocessor, I've already told you, the core extension. This is one among the core extension, different forms, 3 types of core extensions you understood earlier. Coprocessor was one among them, memory management was one, cache was one, tightly coupled memories was one more. Now the special instructions which the coprocessor can execute, they extend the instruction set of ARM processor, and they also extend the additional computational capabilities. And the coprocessor instruction include all these things. There are instructions for coprocessor instruction for performing the data processing, register transfer, memory transfer. Till now, the instructions what we understood, they are the main processor core instructions. Now what we understand is the instructions that can be executed by the coprocessor. Now we are not going to discuss this in detail. We discuss only a short overview of this, because coprocessor is not the main concern here for our discussion. And yeah, and these instructions which we discuss now, they're used only by the cores with the coprocessor. That means all those instructions can be executed only by the coprocessor. If there are cores without the coprocessor, then these instructions cannot be used. Now these are the coprocessor instruction syntax. We have CDP, an optional condition. This is a coprocessor data processing instruction. You got to specify. CP says which coprocessor it is. Basically, for one ARM core, you can have around 15 coprocessors. Here you can specify on which coprocessor the instruction should execute, and what instruction you write here. Say for example, I want a coprocessor to perform the addition instruction. The opcode of addition instruction should go here, and this is, say I want the 15th coprocessor to perform the addition operation. This is the coprocessor number 15 and addition instruction, and I will this is the destination register from the coprocessor. This is the source register, and dash dash dash. And if you want to perform more than one operation, then you can specify one more opcode also. And this is for register transfer, coprocessor register transfer, copying the content from one register to the another register. And this is for memory transfer, transferring something like load and store, which I've already understood for the coprocessor. And again, these things are not required in depth, this, because we focus only on the main processor instruction set rather than the coprocessor instruction set. The CP field, you can just go through. The CP field represents the coprocessor number P0 to P15. That means I told around 16 coprocessors you can have. So this CP can be P0 to P15, and opcode field describes what operation to take place. CN and CM and CD field describe the register within the coprocessor. So all these things, they define the registers within the coprocessor. The RD is the register within the main core. RD is the main core, and any register which is starting with C is the register which is found in that particular coprocessor. So now one coprocessor example what we are taking is CP15. So is the coprocessor which is reserved for system control purpose, such as memory management, write buffer control, cache control, identification register. That is one coprocessor. And I have an example here, MRC, for transferring the content of this register C0 of CP15 coprocessor to R10 register of the main core processor. This is how you do it. So now what happens here, the C0 content of coprocessor CP15 gets copied to R10 general purpose register of the main core processor. And who is doing that? The coprocessor number 15 is doing it. Now the last thing in this is loading the constants. In ARM there is no instruction which can move a 32-bit constant into the register. That is what I was telling you. Using move instruction, you can move only an 8-bit number, that is 0 to 255. And there are few numbers which you can move even more than 255, but all numbers which are greater than 255 cannot be moved to the register using the move instruction. Now, in order to aid this, support this moving, loading the 32-bit value into the register, we have used LDR. Whenever the number which you want to move to the destination register is in the range 0 to 255, we were doing that using directly the move instruction. If it is greater than 255, then we were avoiding using the move instruction, and we were using LDR. LDR stands for load constant pseudo instruction, which you already know. This is how we wrote it. And apart from this LDR, there is one more instruction called as ADR. LDR stands for load constant and ADR stands for the load address. RD is equal to 32-bit relative address. This is what it loads. Now this I already showed you in one of the program. This is ADR R1 comma text. Now what this will do is this will load the starting address of this string to the register R1. Now it is not the constant which is getting loaded into the register R1. Instead it is a 32-bit address that is going to the register R1. Yeah, this is the last thing in this. Hope you people understood. If you have any doubts, you can mail me. I'll be sharing along with these videos a Google form. The moment you watch this video, you fill the Google form and share any of your doubts to me through the Google form or through the Google classrooms. Okay, thank you.